Good afternoon, everybody, and good evening for some. And today, I hope everybody is okay, healthy, mentally and physically, taking care of yourself and your partners. So today we have the pleasure to have with us Christoph Schäfer. He is from the University of Tübingen. Dr. Christoph Schäfer got a degree in physics and a PhD in philosophy in the field of computational physics and theoretical astrophysics. And now he is a postdoctoral researcher at the University of Tübingen. And he is also coordinator of master program in astro and particle physics. And he is mainly the head of the numerical particle methods group at the Department of Computational Physics. So we have, I think, started about 3 years ago, I think, a kind of collaboration. And we received one of his students, and we have now one student of us there. We had others already going there. And we have starting a small collaboration, but now it's getting very strong. And we have several students and collaborators that are working on SPH programs. That it is a program built by Christoph and his group. So we hope to last longer this collaboration, get very, very good results from that. So today we have the pleasure to have you here, Christoph. And Christoph is going to talk about realistic water transport, late stage accretion. So please, the podium is yours. Feel free.
Okay. Many thanks, Ozun, and also many thanks for this nice invitation. I would be happy to be with you, as I already said, right now in person, but these times are, hard, but at least we have the opportunity to talk online, right? So I will present you today the results of another ongoing collaboration that we had or have with the University of Vienna. And I think that our collaboration, as we will maybe see in several years, will be also produce such nice results. So in principle, this was work that is, it goes back until I think 2012, when we had the first meeting with Rudi Dvorak in Vienna. And they had a nice special research program, which was called Pathways to Habitability. It has already ended, and all these people, Thomas Meindl is now a freelancing scientist, and well, Rudi Dvorak is still active, but he's still active. Akush Basho is also again back. Christoph Burger did his PhD in this program and is now with us here in Tübingen, a postdoc. So most of the results that I will present in the course of this talk are based on Christoph Burger and our work here. You see here already two nice pictures from the Blue Marble project, NASA Visible Earth. And as you see here already, we have a lot of water on the surface on the Earth. And in the context of this pathways to habitability, we realized that water is essentially important for life, as you know. And one way we wanted to find out, how does the water get finally during the planet formation process in this late stage accretion phase to Earth. So for the next hour, the outline of the talk that I want to give here is we will start with an inventory. So if you want to know if you want to model how something came to Earth, you first have to know how much water you have on Earth. So we will talk about the abundance of water on Earth. Where is it? And one other important question is, when did it come? Did it come very early during the formation phase, or did it come late? This will bring us a little bit, one slide on the formation of the solar system in the context. So the model for the water delivery to Earth makes only sense in the context of the solar system formation model. And then we will take a look on observational constraints. So what do we know from observations? Where could this water come from? And then I will come to the things that we do and you do, this modeling. First, modeling of the late-stage accretion process with water transfer, the simulations that Sean Raymond did, Kevin O'Brien, so almost, I think, 15 years ago now. And then from this, I will come to the simulations that we do mainly here in Tübingen, simulations with SPH, smooth particle hydrodynamics, where we can model collisions between large gravity-dominated bodies. And this will bring us to the end to a framework that Christoph Burger developed together with us, where we can now, or where we think we can model this late-stage accretion process with a somewhat more realistic water transfer. Okay, but let's first take another look at a nice picture from NASA, the visible Earth. And here, Otto, as you said, I think you're somewhat over there, right? So here, if you can see my cursor.
Yes,
and
yes.
I'm sitting currently here. I think I can zoom in here. You know, this is Italy, and I'm northern of the Alps here in southern Germany. So this is where I am. It's nice, right? Okay, but you see here a color map of the ocean depth. So you see here on the right-hand side near Japan, the Mariana Trench, deepest place on Earth with, I think, 10 kilometers or even 11 kilometers deep water. And here the Atlantic Ridge between in the Atlantic. And overall, we know we have about 70% of Earth's surface covered with water, and we know the average depth of the oceans is about 3.5, 3.6 kilometers. So this makes in total, you can sum all this up, water ocean mass of, let's say, 2 times 10 to the minus 4 Earth masses. And this is what is called an Earth ocean. So if I talk in the proceeding further now about an Earth ocean, then I always refer to the ocean mass of this. So 2 times 10 to the minus 4 Earth masses. Here I have credits from Howard Perlman, a nice picture. When you put all the Earth on, all the mass, all the water on Earth's surface in one bubble, then you would get here only a circle, a bubble with a diameter of 1,400 kilometers, which is not that much. And this is all the water, all salt water, the water in plants, animals, in us. And if you just take the fresh water, so the groundwater, the water is in the sea, and the rivers, and not the sea, but the lakes, of course, in the rivers, groundwater, then you get bubble is a little bit smaller. And if you take only the water that we can drink, so the water that is accessible in rivers and lakes, you end up with this small bubble here, which is only then now with a diameter, I think it's about 30 kilometers. So water is very precious. But as it turns out, if you talk to geologists or geophysicists, then most of the water is not on Earth's surface. There is also water in Earth's mantle and water in Earth's core. So if we look at the abundance of water on Earth, you have also to consider the interior. And we have a heterogeneous distribution of water because we have this planetary differentiation into Earth's crust, mantle, and the core. You see here the very thin crust, then a mantle, upper and lower mantle. We have here the outer core, which is liquid, and then the solid inner core. And these different regions can bear different amounts of hydrogen or water incorporated in these silicate minerals that constitute the planet's crust and mantle. So if you want to know how much water is on Earth, you have to look also at these mantle and core. If you zoom in here, you just take here this small layer. There's a nice sketch where here we have the crust. There is all this plate tectonics happening on this thin crust. We have here these volcanoes. Then we have the very dry upper mantle, which contains olivine. And if you go to a depth of about 400 kilometers, Here, this olivine does a phase transition due to the pressure into wachsleiite, and this wachsleiite can bear up to 2 weight% of water. So we have a quite hydrous zone in this so-called transition zone, which goes down to approximately 700 kilometers, where then the pressure is so high that ringwoodite, which is another water-bearing mineral here, turns into bridgmanite. So in this hydrous zone, you have wachsleiite and ringwoodite, which can have a lot of water, and in total, currently it's thought that this small layer here, this hydrous layer between the upper and lower mantle, can bear up to 3 Earth oceans in total. Okay, and then we have also the lower mantle, which goes then down to the core and contains bridgmanite. Okay, we know this principle from earthquakes and seismic data, where you can see this transition zone. I mean, the viscosity changes in this layer. The change of viscosity makes a change of the sound speed. You get reflections in the seismic data. And we find this transition zone all over the globe in approximately the same zone. I'm not an expert on this, but there's a lot of data coming from geology and geophysics. We have also, since 5 years now or 6 years now, information from so-called deep diamonds, ultra deep diamonds, because by volcanic activism, some diamonds can travel up to the Earth's surface. And I have here a picture from a paper from Pearson, here 2014, where we have here a diamond, which a very small inclusion of ringwoodite here, which is only several micron, I think 40 micron size. And you can measure, in principle, the water content of this, and as it turns out, it has indeed up to 2% weight% of water. Okay, it's getting even more complicated or unknown if you go deeper. Apparently, there's not a lot known about in Earth's interior, so we sometimes we know more about the surface of the moon than of Earth's interior. And the current estimates of the budget and distribution in the interior have very large uncertainties. So in principle, we don't know if there's any water in the core or very much water. And recent experiments here, I cite a paper by Tagawa from this year, and numerical simulations from Lee from last year show that hydrogen can be highly siderophile at very high pressures and very high temperatures, which are approximately abundant here in Earth's core. And siderophile means iron-loving. So this means during the formation, hydrogen fractionites into minerals that contain iron. And as you know, Earth's core has a lot of iron and nickel, so it's totally unclear how much water or hydrogen is in Earth's core. And unless water was delivered only in the final stage of accretion, 0.3% hydrogen, weight% hydrogen can be incorporated in the core, which means up to 7 Earth oceans, 70 Earth oceans, which is, so most of the water can be in the core. So if we do the summary about the abundance of water on Earth, these values are taken from a review article by Anne Peslier. Then we are pretty sure that we have 1 Earth ocean on the surface. Okay, this is quite clear and obvious. We have 1 to 10 oceans in the mantle, which has already a very large error. And then we have none to 70 in the core. If you sum this all up, then you get these numbers. And please keep approximately these red numbers in mind. So this is the number that we want to get if we do a model and do simulations. Then we want, in the end, have something like 0.37 weight% or down to 6 times 10 to the minus 3 weight% of Earth masses. This should be the amount of water that we get out of our model. Okay, so we know somehow how much we have. Now we have two different possibilities. Did the water come very early in the formation process, or did it come late? And this essentially gives us two different models for water delivery, two scenarios. See here on the left-hand side, the so-called wet accretion model. So water is there from the start. You have in the protoplanetary disk some dust and dust grains, and one assumes that on these dust grains there could be water sticking on this. This water could be somehow shielded from the radiation from the sun or the proto-sun, so it doesn't get away. And in the wet accretion process, this wet dust coagulates and directly forms Earth, and you get the water in situ. The other model here on the right-hand side is the so-called dry accretion model. You had no water in the coalescent dust, and the early Earth formed dry, and the water-rich bodies then crashed into Earth later during the late-stage accretion phase, and then finally brought the water to Earth, the dry accretion model. And as you already probably assume now, since I will talk about the late-stage accretion phase, we prefer here in Tübingen this so-called dry accretion model, and I will give you two arguments currently. So first argument, which is in my opinion very strong argument, is that we know now, yes, we think, we're quite sure that the moon was formed by a giant collision where something like, which we call TIA here, collided with the proto-Earth, with Earth. TIA has approximately the mass of Mars, and this very giant impact, which had very severe consequences. There was a debris disk formed in the course of this impact, and out of this debris disk, then the moon was formed. So this is all not to scale, it's just a simple sketch. But you can think that such a giant impact with TIA had approximately, or models indicate that the velocity was about 15 kilometers per second. This, in principle, this impact resets the whole mantle and surface of Earth again, and you lose a lot of volatiles due to a magma ocean formation in the course of this giant impact. And we know that this impact happened approximately 60 million years after the Earth formation, so late in the phase of the Earth formation. Another evidence comes from isotopic measurements. This is more from the geophysicist community. There's a lot of things are ongoing because the experiments or the techniques for the measurements are getting better and better. And these isotopic measurements indicate that volatile-rich material from the outer solar system was delivered late during the late-stage accretion process. Here I cite a paper by Mario Fischer-Goethe from the University of Cologne. There are some strong arguments, I think, for this dry accretion model. There are still good arguments for the wet accretion model, but in the following, I will focus only on the dry accretion model. So, what are then the conditions during the late stage accretion phase? During this dry accretion model, when this took place in the context of the formation of the solar system. So can we find a model that fits into the planet formation model for our terrestrial planets? And within this model, can we show how this water was delivered to Earth? And just reminder, you know all this process of planet formation. We have here first interstellar molecular cloud that collapses. You get by the fact because of angular momentum conservation, you get the formation of this nice protoplanetary accretion disk. In the following, by cooling and coagulation, these dust grains settle in the midplane of the disk, they grow, you get somehow formation of larger bodies. I don't want to discuss about all this pebble accretion or gravitational instabilities, but somehow we get larger bodies, and out of these larger bodies, and with larger bodies I mean bodies in the size of the moon, or let's say protoplanets or planetary embryos in the size of Mars, and these finally accrete then to the planets. And all this water delivery here will take place in this very last phase, in this phase of this late stage accretion phase, which here I put in the context of three main phases in the last phase, where the gas disk has already dispersed. We know that Jupiter has already formed and is orbiting somewhere in the outer solar system, and we have planetesimals and protoplanets, planetary embryos in the inner solar system that have dynamics which are based purely on the gravitational interaction. Okay. Okay, and in the course of this dynamical interaction between the inner in the inner region of the solar system, Jupiter or these more water-rich planetesimals are scattered from the outer regions, from this disk into the inner regions where it's hotter. In the outer regions you have more ice and more water, and this then transfers in the end the water to the inner solar system and gets accreted on Earth. Okay, so can we somehow, from an observational point of view, get an indicator where this water came from? And for this, we have something which we call something like a fingerprint of water, which is the ratio between deuterium and hydrogen. So here the DH ratio in the water, principal heavy water versus normal water. Here you have heavy water and normal water. And this chemical reaction depends on the temperature. So if you have a very hot environment, this is shifted to the right-hand side. You produce more standard water, let's say normal water. If it's colder, the outer regions of the protoplanetary disk further away from the star, you produce more heavy water and standard hydrogen. And you can measure this, the H ratio for different objects in the solar system. And here we have the Earth with the standard value of 1.56 times 10 to the minus 4. And this is called the Vienna standard mean ocean water. Okay, this is a standardized DH ratio. Now we can compare this ratio to different objects in the solar system. And then we know that the Earth, the water from these objects might be similar to the water on Earth. So for example, here, I want to point this out because this figure is taken from a paper by Paul Hartog from 10 years ago. And he found that the DH ratio in Hartley 2, this Jupiter family comet, was exactly the ratio of Earth, which raised people thought then that these Jupiter family comets would be a very good source for Earth's water. Then here, Curie, you know, probably from Karin Altweg, this paper, and Curie from the Rosetta, that we had now a different DH ratio, so it might be unclear how much of the water was delivered by comets to Earth. As a matter of fact, there was also a paper by Morbidelli which shows that from a dynamical point of view, only up to 10% of Earth's water could be delivered by comets, because the probability of collisions is so small. So if you compare now the DH ratio of Earth to the DH ratio that we find in carbonaceous meteorites, then we find that this fits quite well. So the current thinking is that carbonaceous chondrites contain approximately the same kind of water that is on Earth, and this might be a very good source for the delivery of water to Earth. So in total, if we take these observations and the context of planet formation together with the giant impact that formed the moon and the idea that the water was delivered late, we can somehow draw an overall picture, which I try to sketch here. So this is the situation at 1 AU where we are now. And we have very early stage accretion process where the gas was still around in the disk, and the gas was dispersed after several million years. And here we have gas and some water-poor planetesimals because of the high temperature. Then when Earth has already 60% mass accreted, so the gas was already dissipated, we had Jupiter orbiting in the outer regions. We had the proto-Earth here already differentiated, maybe, probably because it was large enough. Then already there were water-rich embryos, water-rich planetesimals scattered inwards. And later on, after 80% of accretion, prior to the giant impact, which is sketched here, we had already water-rich embryos, which means we had differentiated bodies that had iron core, silicate mantle, and then maybe an ice shell. And then in the end, after 70 to 120 million years, we have our final Earth with the water content that we see now. And the question is, can we model this? Can we simulate this all with the computer? And this was done firstly by, I think, Sean Raymond in 2006 and Kevin O'Brien. They used N-body simulations of this late-stage accretion process and added water delivery. So in principle, they distributed planetesimals in a disk with different weight percents of water according to the asteroids that we know now, the water content of carbonaceous chondrites and other asteroids. They put the gas giants here, Jupiter and Saturn, on places where are they now. They assumed eccentric and also circular orbits here, indicated by the dashed and solid lines. And then they just integrated for several million years. If you ask Sean Raymond, then I think the simulation that he ran for his PhD thesis took more than a year on the workstation under his desk. So very long-running simulations. And all these simulations assumed perfect merging and collisions. So as soon as two bodies collide, they just merge and grow. And I've got here a video from Sean Raymond's webpage, I think, where you see here the semi-major axis and the eccentricity, and this is the initial distribution of dry and wet planetesimals. So in total, 2,000 protoplanets or planetesimals with a total of 10 Earth masses. Here's Jupiter, and this is the water content, and this is a video. I hope this works now well with. Yeah, you see a little bit. So this will run for, I think, 200 million years in the end. And you see by the collision, you have a lot of growth here in the inner solar system. These protoplanets growth, a lot of water is lost and they're scattered away. And it's getting faster to the end. Okay. And eventually you see here, look at 1 AU, this is where we are. we end up here with an Earth with 0.3 weight% of water. The estimate, if you remember from the first slides, was 0.37 to the max. So we are in the range. Everything looks quite good. This was a very good result by this model, perfect merging. Here we created somewhat Earth-like planet. Here's a mass which got too big, and so on. But in principle, it worked, okay? So it's on the upper limit of our estimates, and you get from these late-stage accretion simulations with perfect merging terrestrial planets with a very high water content. And people then, in the following, I mean, this simulation was already 15 years ago, and the following, they improved the simulations. They used also just fractions, then added a artificial fragmentation model and so on, and these simulations are now very good. But in principle, we thought then, when we started this project together with Vienna, from the point of view what we can contribute to this kind of long-term simulations, how accurate is this assumption of perfect merging if you have two large bodies colliding? Because we knew from our SPH simulations in the context of planet formation and growth that you can have a lot of different outcomes when you look at collisions. Not only merging, you can have disruption here, you can have partial accretion, where the large objects increase their mass. You can have partial erosion, where you lose mass, or you can have hit-and-run collisions here. And this can be characterized by a so-called accretion efficiency, here xi, which is simply the mass of the largest fragment minus the mass of the target in a ratio to the mass of the projectile. Which means for xi equals 1, you have perfect merging. If xi is negative, you lose mass. If xi is positive, you have accretion, you gain some mass. And for xi equals 0, you have a hit and run, somewhat hit and run collision, which means in principle, the mass doesn't change much, but you can have a transfer of mass between the two bodies and so on. I will show you some simulations later. So the idea was, or when you look at the dynamics of the two protoplanets or planetary embryos colliding, then you find that most of the collisions are hit and run collisions. So where in principle the mass is not changed much, but you can think about if you have a differentiated body. Let me go to the next slide. A differentiated body with an iron core here on the bottom, the red silicate mantle, and then water ice shell, right? And you have a hit and run collision, then the water ice shell is affected the most. If you look at this video here on the top, this is an SPH simulation, just to show what can happen. Then these bodies do not change their masses, but in principle you have a water transfer from one body to the other, and a lot of other different things can happen. You can have also a loss of the water because it just vaporizes. So we thought we could take a look, a deeper look in this kind of hit and run collisions, and especially care about what happens to the volatiles sitting on the outer shell of these bodies. And how do we do this? And this is just only one slide with formula. I know you're probably more used to formula than my usual students, of course, but I promised to do a talk more with videos and not a lot of formula. So these are the equations that we solve. We, in principle, look at the conservation of mass, and the conservation of momentum, plus the conservation of energy. And you see here that the change of density is just simply given by this mass flux here, divergence of the velocity. And here the change of momentum, or here the acceleration, is given by this gradient of this stress tensor, the Cauchy stress tensor, which is composed of two terms. Here, the term with the P with the pressure, which cares about the tension and compression, and then this deviatoric stress tensor S alpha beta, which takes care about the shearing. And if you neglect shearing terms, then you end up here directly with the so-called Euler equation that you probably know from hydro, where you can model or describe an ideal fluid. So the acceleration is simply given by a pressure gradient. So all the physics in principle go in here, in this P and this pressure, because here you need the equation of states. And we, in principle, if you want to model such an object here, like here on the top right, which is cirrus, then you need to have a good equation of state that can describe such an object. Maybe that may depend on the density and the temperature and so on. And for this shearing, if we use this for such large objects, you don't need shearing because they're mainly driven. In principle, they more behave like they have no material strength in this sense. We can easily model them without any shear terms. But in principle, here we add for smaller bodies that we can also model with something which is just the shear modulus times a deformation. And we do this with SBH, and I don't want to give a talk about SBH. SBH is simply a Lagrangian particle method which you can use to transform any partial differential equation into an ordinary differential equation. Then you integrate this ordinary differential equation. I have here on the lower right a difference between a standard Eulerian grid scheme, like finite differences or finite volumes, where you have a fixed grid and your body moves through this grid, and you calculate the fluxes between these grid cells and so on to solve the equations. And compared to this, we have here SBH. We divide your computational domain into single particles, and these particles can then exchange momentum and energy. And here in Tübingen, this is in principle all kind of simulations that we do. We can model with SBH now purely elastic materials, here colliding rubber rings. This is a famous test problem from 20 years ago from Joe Monaghan, or even longer. Then we can model granular material. Think about regolith on a lunar surface, which behaves a little bit like sand. We can also do hydro simulations. This is a circumbinary disk of a circumbinary. I think this was Kepler 16. Here we have modeled the formation of Arakoth, here a collision, and here we have a special porosity model because these objects are highly porous, or at least we think they are. And so on. And this is all in principle done with one code only, with this Millipar-Kuda code, which is developed by the numerical particle methods group here. And I have here a nice picture from one of our Christmas party before the pandemic here. Current members, Patricia and Raphael, are here printed in bold already. So this was the group then, before the pandemic. And here's the group, how we meet these days with Zoom. We hope to have the group together next week, so for the first in-person meeting for a long time now. In principle, we have different research topics. So some of us work on the development of the codes, some more or less focused on the computational side. We have also started implementing a new version of the code, starting from scratch. So it depends on how long this will take, but we will have hopefully a faster version of the current code. Then we have people who implement new models, such as the porosity model that was implemented by Oliver Wandel. And then people who just do simulations, like Hugo, who does the simulations on circumbinary disks. Yes. And with Raphael, we will do nice simulations in the context of exomoon formation, I hope. So with this code, we took this code and took a deeper look at what happens to the volatiles, or especially to the water, in such hit-and-run collisions of protoplanetary embryos. And this was done basically by Christoph Burger together with me 2 years ago. So we took our SBH code with self-gravity, we took the Tillotson equation of state, we used no material strength, and we varied the impact velocity between the two bodies, we varied the impact angle and the mass ratio. In principle, we used only one total mass, approximately the moon mass, but we added also 2 different masses just for comparison. But we focused in principle really on the size, approximate size of planetesimals that we think we have also in this late stage accretion phase. Okay, and so what did we get here? We've got here 3 different kinds of simulations with just slightly different parameters. We have here a mass ratio of 1 to 9. And if I zoom in here, then we have here the velocity, collision velocity was here 2.5 times the escape velocity, and an impact angle of 45 degrees. Remember that 0 degrees is a head-on collision, and 90 degrees would be a total oblique collision. Here we have a hit-and-run simulation. You can, if you analyze this simulation more, look at the data, then you see that these 2 objects hardly change their masses. And if you lower this impact speed, you use an escape or an impact velocity of 1.5 escape velocities, and you lower the impact angle, you get partial accretion. So this bigger body increases its mass. If you increase the impact speed to 4.5 escape velocities and leave the same impact angle, then you get partial erosion. And this body loses a lot of its mass and most of the mass of the outer shell. Okay, so this just, we did, I don't know, 50 or 60 of these simulations and then analyzed. And here is a figure from the paper where you see the total water loss. So all these dots and points here in the simulation, we have the total mass of this moon mass approximately, and gamma is the ratio between the mass of the projectile to the mass of the target. You see here on the x-axis is always the impact speed in units of the escape velocity, and on the y-axis it's the total water loss in percent. And please note that the y-axis have different scales here. Okay, this is always a different scale from figure to figure, and each panel shows a different impact angle. So for example, if you go to a head-on collision here at an impact speed of 4.5 escape velocities, you get here a water loss of 100% if you have a mass ratio between the projectile and the target of 1 to 2. Okay. If you have more oblique collision with an impact angle of 60 degrees, so this is something like this probably, and you go to the very same impact speed, you end up with a water mass loss of only somewhat between 9 and 10% for the same mass ratio. So it strongly depends on the geometry of this impact angle in this case. Okay, you see here, for example, what else can you see? That for this very high oblique impacts, you can also lose almost no water in a collision up to 3.5 here escape velocities of impact speed. If you go to the individual picture, so here we're not interested in the water loss of both objects in total, but in the individual water loss between two of the two objects here. Then I've got here a sketch where the figure in the color indicates the water mass fraction. The initial water mass fraction is 0.1. So before the collision, all these objects have the same initial water mass fraction. And you see in this plot, depending on the impact speed, units again of the escape velocity, and the impact angle, you see here now the water content after the collision of both objects. And you see also the size of the object indicates, if I zoom in here, maybe here, you see here this grayish area. This was the size of the object before the collision and after the collision. So two examples here zoomed out. We have here oblique collision with 45 degrees at an impact speed of 1.5 escape velocities, and you see that the water mass fraction of both objects hardly change, and only the larger one, the smaller one, loses some mass. It's getting a little bit smaller. In the other case, if you have a high velocity impact head-on collision, then you see both of the particles lose a lot of water in the course of this collision, and the smaller one loses a little bit less than the larger one. Okay, you can read a lot of things or take a deeper look and an analysis. Another thing, if you look at simply this setup where you increase the escape velocity, the impact velocity at a given impact angle of 45 degrees, then in principle you see that the higher the impact speed, the higher the water loss. And what you see here also is that always the smaller object loses more water. Okay, in all cases here you see that the larger object in principle has the same water mass fraction after the collision, and only the small object is affected more. So in the beginning of this project, we thought that we could somehow derive, let's say, scaling laws or a collision map or something where we can somehow give an input to other n-body simulations where you can simply then, when you have a collision in the n-body simulation, you can use a lookup table, and then we know out from this simulation we can say, okay, you have this and that outcome and water loss. But as it turns out, we found, okay, you lose water if the water loss increases when you increase the velocity or you increase the mass ratio, and the water loss decreases if you increase the impact angle. And the outcome really strongly depends on all different kinds of parameters of the simulation. So impact velocity, impact angle, and the total mass. So the water fractions practically never increased as long as the initial water mass fractions were identical. And what we also found out was that you can have very high significant loss in some single collisions. What we couldn't derive there 3 years ago was some scaling laws, like, for example, if you think about the paper by Sarah Stewart and Zoe Leinhardt, who found very nice scaling laws for planetesimal collisions, which were gravitationally interacting. And for us, the outcome was too diverse, so we couldn't do this. This was 3 years ago, and then we thought, okay, what could we do? We sat down, had a meeting together with the guys from Vienna, And then we had different ideas. So first one was, again, we just interpolate collisions. We do a pre-computed catalog. We had a lot of simulations. We did a lot of low-resolution simulations. Thomas Meindl was the PI of this project, and they did a paper with David Bensonon in 2017 based on this pre-computed catalog. So this also worked quite well. The other possibility was we just do an n-body simulation, and then we see what collisions take place, and then maybe we do a post-processing step and simulate these kind of collisions with an SBH code. Then the original idea that didn't work out was these scaling laws, which Zoe Leinhardt did, and Sarah Stewart or Robert Marcus here. And then I read a paper by Genda, and he proposed, why don't we just do an SBH collision simulation whenever a collision happens in the n-body simulation, right? And in these days, Christoph Burger paid me a visit in Tübingen. We talked. In principle, we wanted to do a totally different thing. And in the week that he arrived, there was a new paper on arXiv, which covered exactly what we intended to do. So we thought, okay, this could be a nice project to do together. And we took Rebound. Probably you know the Rebound code by Hanno Rein, and combined this with our SBH code. So in principle, Christoph Burger sat down, wrote a new code. Initially, we thought that this is just, in principle, an easy Python script that does this link, the interface between the two codes. But in the end, I think it's now, this code has probably as much lines as Milo Barracuda itself now. But the idea is we run a standard n-body simulation, and each time Rebound recognize a collision, triggers the collisions, we just do an SBH simulation on the GPU, and then we track the results, or we analyze the fragments of the SBH collision and just track the two largest objects, or only one single object if we have perfect merging in the end, and then feed these back to the Rebound code. And this runs all automatically. This runs now quite well. And in principle, I think we have also one workstation in Tübingen that does nothing else than running Rebound for years now. And if you keep the number of particles quite low, so 75,000 particles is not a very high resolution, then this simulation can be done in 1 hour on the GPU here. So in principle, the main computation time still goes into Rebound, and the SBH simulation is only 1 hour. So we did this then for this project, and it was published last year. And we initially, in principle, took the very same initial conditions than Jean Raymond in 2006. So we have, again, this picture with the two gas giants. We have different planetesimals and planetary embryos with a different initial water mass fraction here in the interior. And we had two different models, a lower resolution here with 35 embryos and 150 planetesimals, and a high resolution just for comparison. And I think now we have even higher resolutions running, but they are still running. And I want to show you now, in principle, the exact same movie that I showed you half an hour ago. And here now with this hybrid code, this framework, Rebound coupled with SBH. On the right-hand side, it's only Rebound, and on the left-hand side, it's with our SBH collisions. You have here also here Jupiter and Saturn, and here the same distribution as we had before. And these are also, again, two videos. You see here, or you will see that the video on the left-hand side will run much longer than on the right-hand side, simply because we don't have perfect merging. We do have perfect merging if we really find perfect merging, but in principle, for one collision, and on the left-hand side, we still get two bodies. So we have to integrate much longer until the whole model converges, and we get a result in principle. So you see here that compared to this perfect merging simulation on the right-hand side, we in principle produce bodies with less water mass fraction here on the left-hand side. We did a lot of different, or CB, Christoph Burger did a lot of different simulations. We found a lot of collisions. Here on the left-hand side, you see the collisions or the dots from all collisions during these 18 simulations that we done for the paper. We had different models here. CJS is for circular Jupiter, Saturn, and EJS is for eccentric Jupiter and Saturn, where they have the eccentricities that are observed now. And here PP1 and PP0 gives or corresponds to two different treatments of the planetesimals. So in one case, the planetesimals can also collide. In the other one, they don't collide. There we use the planetesimals only to get the dynamical friction. Okay, and you see here, we get in principle all kind of different impact angles and impact velocities in the range up to, well, several here. This is, 12, 20. Here escape velocities. But in general, you don't see this on the picture, but if you analyze this, about 50% of the collisions that we found are really hit-and-run collisions. And this is in very good agreement with with other simulations by Zoe Leinhardt, for example. If you look at the evolution of collision velocities, then you see that, please note the logarithmic scales on both axes here. You see that initially we have very quiet distribution, probably from the initial conditions. Then we have a phase where a lot of collisions take place. Here, the larger dots are collisions between protoplanets or protoplanetary embryos, and the smaller dots are collisions between a protoplanetary embryo and a planetesimal. That's why you see here two different sizes of these dots. And then after here, this was the longest simulation, 200, 300, 500, 600 million years, I think. We have all converged in principle and get a stable planetary system. If you look at the total mass in the system, again, compared to perfect merging simulations, on the plot on the left-hand side, you see the perfect merging simulations are dashed lines, and the SBH coupled simulations are solid lines. And you see that the SBH simulations lose a lot of more mass because, of course, in our model, we only track the two largest objects. So we are not really conserving mass in this model. And we lose much more mass than the perfect merging models. Since we were, the origin of the whole project was about pathways to habitability. So in principle, we thought about the content of water of planets formed in the habitable zone. So if you look at the formed planets between 0.7 and 1.5 AU out of our 32 sims, then you see we can form, or we see in these simulations, in all these simulations, I said also this perfect merging simulations are also quite good, that we get planets with masses with enough water here at 1 AU, but I think we have not enough planets to do real statistics here. Yes, so I think we will need more data to do here a little bit of better analysis. Nice thing is what we can do with all our simulations, that we can really take a look at the history of one planet or one object during the whole course of the simulation of several hundreds of million years. So we have here the water content over time of one individual planet, which in the end turned out to be a planet at 1.1 AU with a mass of 1.2 Earth masses and 24 Earth oceans, which is in principle what we want, or what fits quite well to our estimate. And you see here two lines, the solid line, which is the outcome with simulations with SBH, and then a synthetic perfect merging simulation where we added just all the water loss also to this body. So you would end up with a water content of, I think here, more than 80 Earth oceans if you do perfect merging. And you see here the crosses are the water mass fraction of the other body, which is in the collision. So, for example, here we have a collision with a body with a very low water mass fraction. Here we see we lose a little bit of water. Here we have a collision with a body that has a much higher water mass fraction. And what you see here, or what is most striking in this plot here, I think, is that the water content can change significantly with just a few collisions. Again, note the log scale here on the y-axis. But what we can do now is we can look at this data, and then we can go into the simulations, or can directly look at the simulation. What happened here? Here we have a simulation where our body gained, I think, let me zoom in here with impact angle of 48 degrees. And I think here we gained 3 Earth oceans in this single event. And then we can analyze this and take a look at the simulation and see directly what happened. We had here a very body with a very high water mass fraction, which lost a lot of its shell now to our object. Okay, and we think now that we can model quite, I would say, in a good way, quite accurately, this water delivery in the late stage accretion. Our simulations support also the tri-accretion scenario, like the simulations that are done by other people, Raymond initially. We find that most similar sized bodies here are collisions, or similar sized body collisions are collisions in the hit and run regime. And the water content is really set by only few or even only one collision. So in principle, we are quite lucky here that we have exactly the amount of water on Earth that we have, and not 10 times more also. We think that this whole tri-accretion scenario, that the water originated from carbonaceous chondrites, planetesimals, and was delivered in the last phase of Earth formation here, fits quite well. Of course, this is in principle, I mean, this project is ongoing now for years, but as you know, we're never done. There's still a lot of things to do. As always, computers getting faster, graphic cards getting bigger, so we can, in principle, improve the resolution. We are on the lower end of this resolution. But on the other side, we have already so much data. Okay, we have now more than 10,000 collisions from over 2 years of simulations. And what we do currently is that we, look at this data and search for different kinds of things like the formation of moon. We can investigate ejections from the solar system. And we had some people from the ML community, machine learning, that approach us and want to use these catalogs to train for training data. Let's see what comes out of it. But of course, also from the physical model, we are not quite satisfied. So there's still room for improvement. For example, as I said, we lose a lot of mass because we only track the 2 largest fragments. So we think about that we will somehow create a hybrid model where we have a density distribution generated from these fragments and so on. So there is still improvement. And of course, as I said, a statement that normally is used in all talks that use computational astrophysics is that we can always have higher resolutions. So currently we run some interesting collisions here. We have now, for example, this is now with 1 million particles, a collision of two bodies where the total mass is again here in the moon range. And what was the impact speed? I don't know anymore exactly, but you see here, this in the end turns out to be a perfect merging simulation. And you see here that a lot of things, interesting things can go on, a lot of formation of fragments or droplets here. So currently we rerun some of these simulations in a higher resolution and to get some further insights. Okay, principal, how am I? The time, it's okay, a little bit long. These are the references, and I hope. Okay.
Okay, good. I think that was great.
Okay.
Great presentation. I think it's very dense. I think more than a decade of work. So
only 2 papers, so only 2 papers.
but I think it's a kind of investment. Now you have the machine, you have the code, so now you can collect the fruits. I think you have a powerful code that it's very important. So now we are open for questions or comments. Anybody would like to make a question or a comment? So Ernesto, please.
Hi, Dr. Schäfer. Very nice presentation. Thank you very much. I want to understand how you build the SPH particle. The water is made in layers or are heterogeneous in the particle?
Okay, yeah, in principle, we set up, this is a little bit tricky to set up the initial conditions for the SPH collision. When you get the information from Rebound that you have a collision between 2 different objects. And we know the water mass fractions of these objects. And we always assume that the protoplanets or the embryos have this iron core, then this silicate mantle, and then the ice or the water on the outer shell. So they are always differentiated perfectly. And even if they have, I mean, these objects then in general have collisions, up to 20 collisions or so during the whole simulation of several million years, several hundred million years. And but the time between 2 collisions is normally long enough so that we can safely assume that we have the original perfectly differentiated embryo again. So it's always an iron core, silicate mantle, and then the icy shell.
Okay, so there is more layers of material.
Yes, in principle we have always 3 layers.
Okay.
And then we set this up that these layers are in hydrostatic equilibrium. And then we use in general a distance that is long enough that you also get already the tidal effects and tidal heating, tidal effects from the collision. Yes. Because these make, so it's a little bit tricky to know when the collision has ended, okay, and how to the initial distance between the 2 objects.
Yeah, I understand. Thank you very much.
Okay, thanks, Ernesto. Anybody else? Well, Rafael, go also. Rafael.
Hi, Christoph.
Hi, Rafael.
A nice talk. Just a question. How can you guarantee some kind of consistency between Rebound and SPH? How do you know that things are going well when you switch and go back?
Okay. You mean that we conserve energy and momentum and everything?
Okay,
so in principle, yeah, since we lose mass, right? So we are not exactly conserving all the things we want, but the fragments at the end are. I mean, Christoph Burger has. I mean, most of the part of this code is making sure that the values are conserved well. So. He calculates. How does he do it? The thing is that he sets the two largest fragments back into Rebound so that the angular momentum is conserved. So we lose mass, but the angular momentum is conserved.
Okay. And just another quick question: do you have to do some sort of relaxation of the bodies between? Make the collision, or it's not necessary?
No, this is not necessary. In principle, I mean, we set up the two colliding bodies in hydrostatic equilibrium. This is quite well. This works quite well. And then after the collision, in principle, from the experience, it's 5 times the time. The passing time which we would have without a collision is in principle a good indicator that the collision has ended. So if you end up with perfect merging or something, and then we do a fragment search all automatically, where we analyze which fragments are gravitationally bound to the other object and feed this back into Rebound. This works quite well. Yeah, I think the main error really comes from the fact that we do not conserve mass. This is something that we want to get rid of.
Okay, thank you.
Okay, thanks, Rafael. Well, I have a question. It's more like a philosophical question in terms of when you use SBH code for a problem. This one, for instance, related to the collision and loss of water. How dependent is your results on the settings? I mean, when you fix the material porosity, so I don't know, some settings, parameter settings inside the SPH code. How dependent is on that? If I am going to use another model is it highly dependent or it's not? It's just some final adjustments.
If only I knew, right? Okay. I don't think that there is a short answer to this question. I mean, in principle, let me put it this way. So these kind of simulations of collisions, since they are pure hydro and we have no material strength, make it already easier, okay? So we have no porosity involved here. In principle, we have equation of state. Until it's an equation of state that originates from impact experiments, we can now use also different equation of state ENIOS, which has, should give better results and higher or better convergence even for a lower number of particles. In a sense, I think that these simulations have an error of, I mean, if you change numerical parameters, error of less than 5 or 10%. So, I mean, it all depends mainly on on two factors. This is the equation of state and then also the resolution. And already the equation of state is very scarce. You know, I mean, if you want, so we model water, and if you, I mean, maybe you probably know that even to find a good equation of state for water is already complicated. So we use a very, let's say, simple equation of state to model water itself. So from the numerical point of view, I think we have good results. So I have to come to a point and see this here. From the numerical point of view, I think we have good results, but the physical model, of course, can be improved much more. Okay, I think that would be the statement that I want to, in the end, give you.
Okay, so numerically, you are not losing too much. That's the point.
Yes.
Your results are reliable, I think. You have a error bar that's not more than 10% or something like that.
Yes, I mean, we did convergence tests, especially because we use a very low number of particles, right? We have here, I think, 75K particles, and there are people out there that claim that this whole problem doesn't converge until you use at least zillions of particles, okay? But we did, in this 2018 paper, also simulations with 2 million particles, and we saw that if you simply look at the fate of the volatiles, then this low number of particles is enough to give an estimate. I mean, these are not perfect values, but it's better. It's okay.
Okay, yeah, depends on what you want. For what you want, that's fine. Okay, good. So I know it was a tough question, but the idea is to have a kind of your perception from that. Okay, good.
Yeah. I mean, the good thing is really that we don't need a porosity model for this, for example, because then you add up much more material parameters that are unknown, right? So it's from this point, it's a very simple SPH physical model for this simulation. Just pure hydro, and then
Okay, good. Okay, thank you. So anybody else? Patrick, please.
Hi, Christoph. Very nice talk.
Hi, Patrick. Thanks.
My question is about how long after the SPH collision you said the bodies are ready to go back to Rebound simulation, and how to select the amount of particles that come back to simulations, Rebound simulations again.
Okay, so in principle, we found that just from the experience from the simulations that about 5 times the passing time that we would have without the collision is enough that you get, in principle, we know that the collision has ended. And what we do then, that we start a fragment search. First, we have a lot of SPH particles, and then we do a fragment search, which particles are gravitationally bound to which object. We start with a large object, and then we check which SPH particle is bound to this object, which will eventually end up on this larger body. And we do this until this algorithm converges, and then end up with the 2 largest fragments, which we feed back into Rebound.
Okay.
I hope this answers the question.
Yeah, sure.
Okay, thanks, Patrick. So anybody else? Any further question or comment? Okay. So good. Thanks again. It was a very nice talk. It was great to have you here.
Thanks, Otto. I will stop sharing my screen here now.
Okay.
Stop. Okay.
Okay. Thank you.